Hello, my name is Greg Risteban. I'd like to welcome everyone today to this Olympus webinar titled Modern Advancements in Conventional Ultrasonic Instrumentation for Improved Inspection Quality. This webinar will examine, among other things, digital technology advancements that have greatly enhanced pulsar and receiver design in modern flaw detectors, and increased computing power that has improved onboard and integrated reporting capabilities. Our presenter today is Coleman Flanagan. Coleman is the Senior Product Manager for Olympus Ultrasound and Phased Array Flaw Detectors. He has over 10 years of experience in the NDT industry, managing global support, training, and resource materials for ultrasound products, and he is responsible for the future development of Olympus Ultrasound and Phased Array Flaw Detectors. This informational webinar will last approximately 1 hour. If you have questions, please type them into the Q&A panel in the lower right portion of your screen during the presentation. The chat panel is not monitored for questions and answers. If we are not able to get to your question during the live event, they will be addressed personally either by email or phone after the event. Now, without further ado, I'd like to turn the presentation over to Coleman. Coleman, take it away.
Thank you very much, Greg, and welcome to all of our participants to this webinar. We appreciate you taking the time to join us today. The topic today that we'll be discussing, as Greg stated, is modern advancements in conventional ultrasound. It's a bit of a lengthy title that we've given to this webinar, and at first glance, the subject matter may actually appear to many to be quite basic. But my hope for you is that by the end of the webinar, you'll have found that there actually have been some very interesting developments in the last 5 or 10 years in conventional ultrasound. And in fact, there may be things that are very common to current ultrasonic equipment that you may not even know about. So we'll begin our survey of these enhancements right now. Conventional ultrasound, as most of you will probably know, has been around and established in the NDT market, in the inspection market, for decades, really since, in some capacities, since the 1940s, and certainly evolving since then to current day. And so, as a very well-established inspection technique, there, on the surface, may seem to be very little that could actually progress and be enhanced about the core technologies for conventional ultrasound. With regards to flaw detection and ultrasound, we know that sound goes into a part and it reflects back. We know that to calculate a thickness measurement, there's a very simple equation looking at the round trip of that sound. We know that A-scans or waveforms on the screen, they'll show the relationship of distance and the amount of energy of that sound as it makes its round trip. We know that reflectors are positioned on graticules, and this provides visual orientation to the inspection that's occurring. And we know, of course, that for angle beam inspection, this creates shear waves, and this allows us to do things like weld inspection, crack detection, and many other applications. So this is obviously just a basic summary, but again, it seems like everything's been covered. So what could possibly be new and exciting about conventional ultrasound? Well, it turns out lots of things. There's actually a lot that we can be excited about, even in the conventional world, without having to move into some of the newer disciplines that are a little bit more of, we'd say, a hot topic like phased array. And really, there have been huge improvements in even the core functionality. And when I say core functionality, really I'm referring to pulsar technology and receiver technology. So we don't really even have to go too far into digital processing of algorithms, special sizing techniques, other high-level or sophisticated features to see improvements in conventional ultrasound, even in the last 5 to 10 years. And there are some very significant advantages of the digital equipment that's in the market today. that support not only the ultrasonic and the acoustic inspection of materials, but also will support the entire workflow surrounding an inspection. So it's not just the measurement. So these are some of the things that we'll highlight through the webinar today. We won't get into things that are very niche market, small focus. We want to look at really broad topics and, again, core functional improvements that have been made to this technology. So we'll start with core ultrasound, and again, here we're looking at pulsar and receiver technology within mainly flaw detectors, also conventional UT thickness gauges. So to start with pulsing, probably one of the most important components of pulsing is the pulsar power. This is very critical to the success of many applications in the ultrasonic NDT field. Pulsar power will translate really into penetration power. So as we're seeing more and more emphasis on inspection of composite materials, of high-density polyethylene, of Teflons, of coarse grain, stainless or austenitic materials, castings and forgings, all of these may require more significant penetration power than some of the mainstream applications like structural weld inspection. Pulsar power can also determine the flexibility of a particular instrument to a variety of applications. So particularly for service inspection companies, you may understand what your needs are for the contract or the jobs that you are working on today, and the equipment that you have may meet those needs very well. But it's not always true that you know what's coming down later in time and what kind of contracts and jobs will be available to you. And so having instrumentation that's more flexible than maybe it used to be in terms of the types of materials that can be inspected can be a really huge benefit to your business. And then, of course, aside from just penetration power, pulsing power can also affect the ability to be sensitive to particular size reflectors. So one of the things that we look to do is really optimize the use of a certain frequency transducer, and of course frequency is selected by the size and the type of reflector that needs to be detected as part of a flaw detection application. So optimizing pulsar controls really can optimize the inspection, and this is one area that manufacturers such as Olympus have started to focus on more in the last few years in terms of how can we better approach pulsing on conventional ultrasound. Now, a traditional pulsar from many decades ago is a very simple electric circuit. And the basic controls in a traditional pulsar would be your energy level or your voltage level, and also your damping. And to create a pulse, all you really need is a very simple RC circuit, as you see here diagrammed in the slide. The way this circuit works is the voltage is applied to the capacitor. The capacitor here will charge up, and at some point it will discharge, and that provides a single pop or a single impulse of energy that is sent to the crystal, to the transducer. And the shape and the timing of that pulse, that's controlled by the resistance value in this circuit, which is also your damping. So it's a very easy and simple way to deliver energy to a transducer and be able to complete an inspection. Now, many, many years ago, this type of simple pulsar, often called a spike pulse or an impulse pulsar, this was enhanced by adding the ability to tune a square wave pulsar. So you'll see both that are detailed here on this slide. On the left, we have our spike excitation pulse, and this is from that RC circuit style pulsar that we saw before. And on the right, this is a square wave pulse, named, of course, because it looks like a square. And the major difference here is that by exciting the crystal but holding the energy, holding the voltage for a duration of time, on that crystal, we can actually get a more optimal response, especially for lower frequency crystals. So typically you'll see an improved performance, improved penetration power, more optimal response from your transducers that are below 10 megahertz. That's where we start to see some difference. So that may, for some applications, that's on the lower side of frequency, but in fact for flaw detection, that's right in sort of the sweet spot. The major portion of traditional flaw detector applications will work between 1 megahertz and 5 megahertz, especially in weld inspection and petrochemical. So there is actually a very good advantage of square wave pulsing for most common applications. And square wave pulsing has been around for quite a long time. It's not really within that 5 to 10 year period that we've been discussing in terms of improvements, but it definitely is an improvement over traditional spike pulsing. And this is much more widely available today on different platforms. So we'll see not only sort of higher-end flaw detectors implementing this technology, but we also see this now on common corrosion and precision thickness gauges and a wide variety of different ultrasonic instrumentation. So if this has been around for a while, and it definitely optimizes our approach to pulsing, the question, of course, is that it, or are we able to improve on this further? And so what we want to discuss in terms of square pulse is this question of how square can you actually make a square pulse, a tunable square wave pulse. And this is where we've seen some really good improvements in the last, again, 5 to 10 years. So the key to these improvements really has to do with reclaiming some energy and some efficiency out of this pulsar that with more traditional means is lost. What we can see in this diagram of a digitally controlled square wave pulse is that the rise time and the fall time, sort of the active push and pull, is controlled and monitored so that we have very precise and very rapid transitions between 0 volts, which is up on the top of this screen, and let's say in this case 100 volts, which is down towards the bottom. So instead of allowing this transition from between 0 volts and 100 volts to take a certain amount of time, which would necessarily kind of lose some energy as you're making that transition, the more tightly this is controlled, the more efficient this pulse is actually becoming for exciting the transducer. Another thing that we're able to control through newer technology is the overshoot and the reverberation of the pulse. So in more traditional pulsar designs, when the pulse is allowed to return to 0 volts, just like a trampoline or other items that have energy, it doesn't really return exactly to 0 volts and stay there. It overshoots the 0 volt line, and there's some reverberation period where it's returning to its natural 0 volt state. Now this kind of reverberation in some cases extends the width of the pulse and may actually interfere with near surface resolution in a flaw detector application. So controlling that reverberation is a strong advantage to being able to utilize this square wave pulse tuned properly and still achieve very good near surface resolution. So this kind of control really wasn't available in original square wave pulsar designs from, let's say, 20 years ago. This is something that's much more modern, much newer in the NDT world, and it really provides very good benefit. So when using what we would call a perfect square or a very tightly controlled square wave pulse, tunable square wave pulse, we can actually see savings of up to 10 dB in terms of the amount of gain required to bring a certain sized reflector to its reference height. Now 10 dB is a huge savings. When we're looking at, let's say, a difficult application where you're requiring quite a bit of gain just to be able to see what's going on within the part, There are some applications where once you get up to 80 dB, 90 dB on the instrument, you're almost at an unusable level of gain. There's so much amplification that it's very difficult to actually pick out what's a defect, what's just background noise or structural noise. Being able to bring that back down into a much more usable range of, let's say, 60 dB or 70 dB can actually be the difference between achieving the inspection properly and not being able to confidently find, detect, and then subsequently size flaws. So this control over the square wave pulse actually brings a really tremendous benefit to most common flaw detector applications, as well as some very sophisticated applications that maybe weren't achievable through a portable machine in the past. Another key component of the pulsing circuit, or the pulsing design of UT instruments, is the PRF, and this is pulse repetition frequency. And the reason to bring this up, this is typically, in many cases, it's discussed quite a bit about what's really required from an instrument for PRF. And there's a lot of different spec sheets that will attempt to show an advantage with certain high values of PRF or low values of PRF, but the question becomes, okay, what's the real value? What's just outside of the numbers, what's the true value of having an adjustable PRF on your instrument? Now, historically, there was probably more value to this control than there may be today in manual flaw detection. Historically, this was much more of a balancing act. So you've been looking at our clown graphic here to balance those plates. In the context of PRF, if we increase the repetition frequency, if we pulse the transducer too quickly, we may actually induce wraparound noise or ghost echoes within an inspection. So in the screenshot here from the Olympus Epic 650, you can see a standard application at a very low PRF, only 20 hertz, and we've got a nice solid back wall with a little bit of noise along the bottom of the screen. Now, if we take the exact same reflection, same application, but we increase the PRF to just below 2,000 hertz, you can see that there's a really tremendous increase in the amount of noise that's within this system. And of course, this is not really acoustic noise as much as it is phantom echoes or ghost echoes. This is that wraparound noise that we need to avoid. When we go back in history a little bit to analog flaw detectors, one of the parameters that really influenced increasing PRF instead of decreasing it to avoid wraparound noise was the idea that with a CRT display, if you have your PRF too low, it actually becomes more difficult to see the trace, see the A-scan that's being drawn on the display. And this is because with a CRT display, we're literally using a beam of electrons to trace out that A-scan. So when we're refreshing the trace by increasing the pulse, the PRF, we're actually drawing the A-scan more frequently, which illuminates the screen more. So it gives you a better visualization of that A-scan. But this is something that's really limited to just the CRT displays. However, since ultrasonic flaw detection has been so well established for so many years, and there are many procedures that were written decades ago that don't require significant updates. And so a lot of these procedures were actually written around analog flaw detector instruments. And as part of those procedures, many of them recommend using the highest practical PRF when scanning for defects. And part of the reason is simply for A-scan visibility. Well, there are some problems in doing this. First of all, this simply decreases battery life. Emitting the pulses will draw more battery life than if you're doing that quickly than if you space those out a little bit more. As we just explained, this may also cause wraparound noise, and for many procedures, this may be the optimal PRF may be identified so that it's not as big a concern, but wraparound noise and ghost echoing, this is always a bit of a concern, and so we want to be able to decrease the PRF as much as possible to avoid any problems that we might have with this kind of noise. But on another level, these kinds of procedures really lead to sort of an arbitrary debate on specifications. Is a flaw detector that you're going to use for manual scrubbing, does it really require 2,000 hertz PRF, or will an instrument that is only capable to 500 hertz PRF, is that sufficient? What do those numbers mean, and where's the real value that we're trying to get out of these manual inspection instruments? And so really in a lot of cases that very high PRF, or cranking up the PRF, provides very little practical value in what we're trying to achieve, again, for manual scanning. So when we evaluate PRF in the context of a digital instrument, well, digital instruments, we're not using CRT displays, we're using flat panel, either LCD or ELD displays. So in this case, the pixel that we're using to draw, or the pixels that we're using to draw the A-scan, they're either on or they're off. We don't really have the phenomenon of increased PRF will give you more pixels or more replication of pixels or something. It's an on or off scenario. In terms of screen brightness, well, we have a separate control for that now. So you can either increase the screen brightness or decrease it, depending on the environment that you're working in, but that's not tied to this ultrasonic component of PRF. And the other thing to consider is that the A-scan is only ever updated at a maximum of 60 hertz. Almost every flaw detector on the market will give you 60 hertz, but no more in terms of the refresh rate. And this is because it's well beyond what the human eye can detect in terms of seeing the refresh. And so the idea of 60 hertz is that if the flaw detector is able to pick up the echo and you're manually scanning, you're using your visual, you're using your eyes as visual detection. And so you'll scan only as quickly, or you should scan only as quickly as you're able to visually detect a flaw. So PRF for screen visibility, certainly we don't need to crank up or increase the PRF any longer with digital equipment. And so this leaves us really only with the concern about missing an echo if you're scrubbing too quickly. For these kinds of manual instruments, you could argue, it could be argued that in manual scanning, 60 hertz is the highest PRF that's ever required because of this sort of visual response and visual detection. So when we talk about the concern of missing a defect, this is where we may want to increase the PRF just a little bit. In the case that we'll show here, and I apologize for anyone living outside of the U.S. For the imperial units here, but just as an idea, just to give us some context to the numbers here. If we were scanning this plate that has a defect in it at 6 inches per second, and we were using 60 hertz as our PRF, that means that the screen is only going to update, and we're only going to collect data every 10,000ths of an inch of the movement of the probe. If there's a tiny pit or a tiny crack and we're moving too quickly that it's within sort of this margin, we could possibly visually miss the indication. Now this is really not likely with manual scrubbing, but this is one of the arguments towards having PRF higher than 60 hertz, so that you don't miss this kind of indication. And this is what we would see. As we scrub across, we'd see that we're only collecting A-scans at certain positions along this plate, and none of them show the indication of the crack here. Of course, realistically, we shouldn't be using a delay line transducer for this particular defect either, but we'll ignore that for the purposes of this webinar. So, in fact, our digital technology allows us a solution to this problem. And the solution here is what we would call a composite A-scan. So a composite A-scan used at a higher PRF than 60 hertz can really can solve this problem without having to go too much higher on the PRF, but also without having to go back to an instrument that has a CRT display. So if we use the example of increasing our PRF to 180 hertz, which is 3 times the screen update rate, that means that as we're scanning across a plate, for every screen update, we're actually going to be collecting 3 different A-scans. Now, in older digital equipment, the instrument would typically just select one of those A-scans to actually display when the screen updates. It wouldn't be able to display all 3 of those because it can't update the screen quickly enough. And so you'd hope that at least it would intelligently select which A-scan to display. But in a lot of cases, older digital flaw detectors would simply delete 2 of those A-scans, and you'd only see 1 of those A-scans from your inspection. Certainly, this can cause problems because you may actually lose some data in that scheme. So with a composite A-scan, we actually solve this issue. In a composite A-scan, all 3 of these A-scans are actually composited together so that even though you can't display them all on the screen individually, you can still make sure that you're not losing any data. And so what we would see with a composite A-scan is we would collect our first A-scan here, which you can see has no indication. We collect our second A-scan, which has our critical defect, potentially. You know, this is the indication that we want to see. And then we collect our third A-scan, which in this scenario, again, has no indication. So 180 hertz PRF, we now have 3 discrete A-scans, one of which is very important to our inspection that we don't want to lose this data. And with a composite A-scan, we would actually essentially add all these together. We don't increase the magnitude of that echo, the amplitude height, but we're able to make sure that any information from any of these 3 A-scans will be represented on the screen when the screen is updated. So through the use of our digital technology, both with simply by using an LCD or an ELD display, but also with this composite A-scan capability, it really eliminates the need for extremely high PRF just to add value to the core application. But it still allows for some procedures where the PRF needs to be higher than 60 hertz to ensure that you're not going to miss any defects if you're doing rapid scrubbing. So that concludes some of our discussion on the pulsar side of our enhancements. And now we'll move over to the other major core component, which is the receiver side. And one of the most important things to discuss on the receive side of modern conventional equipment is the filtering of the signal. So we've already sent the pulse out into the part. It's traveled through your inspection piece. It's been returned back to the crystal, the transducer, which converts it to electrical energy. And now we need to get this back into the flaw detector and display it on the screen so that we can detect flaws, we can do analysis of the material that we're inspecting. One of the first things that we would like to be able to do once the signal is received back is to filter the signal. And the idea here is to increase our signal-to-noise ratio. We use the example of a grainy material, with some material, whether it's a casting or a forging or whether it's something like a composite material, where you have a lot of structure within the material itself. And that structure, hopefully, is smaller than the critical defect size that you're looking to detect, but it still may be big enough that if you're using a more broad-banded transducer, you may actually see reflections from that structure on the screen. And that can really hurt your ability to get clear detection on what's actually a flaw. So filtering has been around for a very long time, and it's very important to basically attempt to eliminate some of the frequency content that's in that received signal that's not desirable and that's not relevant to your inspection, but still be able to pass through any frequencies that you've selected to reflect and be be sensitive to the defect that you're looking for. Now, filters have historically been accomplished through analog filter chips, like what you see here on the screen. And these work very well. The idea here is that the electric signal comes back from the cable, from the transducer into the flaw detector, and it's passed through this chip, and the chip acts as the filter, so it eliminates some of the noise. The signal, once it's through this chip, it then proceeds on to be digitized, and then that's where the computer takes over, and the flaw detector, digital flaw detector, is able to display that on the screen and make measurements. There are some problems, though, with this analog filter technology. One is that the resulting signal will be inconsistent, and only minorly inconsistent, but it can be inconsistent instrument to instrument, because these are physical chips that are manufactured and they all have tolerances. So what this means is that you could line up 3 flaw detectors, you could feed the exact same inspection signal into those flaw detectors, and you may see a slightly different waveform, or A-scan, on each one of the flaw detectors, because it's being passed through this filter that's not necessarily identical across those 3 instruments. Another major problem for analog filtering is that it's a chip that's soldered and manufactured onto the PC board within a flaw detector. So if your inspection requires a specialized, customized filter that is not available on the flaw detector that you own, to modify or to add a new filter may actually be almost impossible, but certainly it's going to be very costly because it requires a new chip that's soldered onto the board. It's required that the signal is processed through that chip. It's a major overhaul to the design of the instrument in order to allow additional filters. So in many cases, this is something that that an inspector won't even be able to approach. They'll simply have to live with the filters that are available to them and try to optimize the inspection in some other way. So a very strong and powerful solution to this that's been adopted in many flaw detectors since roughly 2005 is the ability for digital filtering. And this is a really powerful improvement to the idea of filtering that we've just been discussing. Digital filtering, the word digital, this is one area where it may sound maybe a little scary to the conventional ultrasound world. But the idea is really the same as a high-end audio speaker. So what we want to accomplish in filtering is eliminating certain frequencies of sound, or at least suppressing them as much as possible. Well, this is the same thing that happens when you're looking at getting a really high-quality response out of the music that you're listening to on your speakers. A more generic brand of speaker will take all the frequency components of the song that you're listening to, and it will push it through a single speaker and cause that to vibrate and create the sound. And you get a mix of all these different frequencies they're not exactly optimized, but certainly you can still hear the music, you can still listen to the sound. In a more high-end audio system, whether it's in your car or whether it's in your home or theaters and etc., what we'll do is take the music, the electronic music, and we'll actually separate that into different frequency bands. And each one of those frequency areas, whether it's treble, whether it's sort of the mid-range or the bass, the lower range, will then get fed to a different speaker, which is really optimized for emitting that sound. And in newer technology, that's all done digitally. The separation can be done digitally so that you have very clear lines between these different frequency components, but now you have a very high fidelity overall experience when that's reproduced on these different speakers, which can be optimized for that range of sound. So really the same technology can be applied to ultrasound. And where the benefits come in here, certainly the consistency and how clean the signal is, the fidelity of the signal is really better, much better than analog filters. We're able to more precisely control the cutoff points where we're eliminating sound or suppressing frequency, and the areas where we're allowing it to pass through. And so those areas, of course, are the areas of the ultrasound that we want to use for our inspection. It's very consistent because it's done digitally, so it's literally done as mathematical calculations within the processor instead of being a separate component to the board that has manufacturing variability. And it's very flexible for those custom applications that I discussed in the previous slide. So here at Olympus, we've had several customers that have come to us over the years that have needed those more customized, more focused narrowband filter sets. And with this technology, we've been very readily able to supply that. And in fact, all that's needed is really to program these filters, again, using math, basically using algorithms, that can get added to the firmware, to the code that goes into the flaw detector, and it can be emailed or sent through the web so that a simple upgrade of the unit will now allow access to those filters. So it's much, much more flexible than what's possible with analog filter, and it's really improved quality. It's much more precise and clean way to get a high fidelity signal out of your flaw detector. So this has been a really excellent improvement on the receive side of the flaw detector and the conventional ultrasound instrumentation in the last 5 to 10 years. Now, another major component of the receiver side of the instrument is, of course, gain. And in fact, gain is probably one of the most fundamental, the most important adjustments on an ultrasonic instrument. Gain is something that's changed live. It's very, very common to do dynamic and continuous changes of gain as you're going through a standard inspection, because we need to bring any potential defects or even backwall signals to sufficient height that we can feel confident in the way that we're examining and characterizing and using that for a sizing technique. So changing gain is a very live experience, and it needs to happen during the inspection, not just set up ahead of time. It's setting the amplification of that live signal, and it really takes two good hands. So as in the picture that we see here, one hand is going to be on the instrument, whether you're holding it or whether you're just making adjustments while it's on a bench top to that gain. The other hand really needs to be holding the transducer in a static position. And really the important reason for this is that in most procedures, it's not enough to simply peak up the signal to find that static position and find where the echo height is at its highest. But in order to compare it to anything, we really need to amplify or to attenuate potentially that signal so that it's at a reference height. And now we can actually compare it to a known, probably in many cases just a side drilled hole from a V1 or an IIW block. But at least it gives us some level of comparison. So in order to bring that signal to the proper level, of course, we need to make an adjustment to the gain. Now, there are a lot of examples where peaking that signal and holding it in a static position, holding the transducer exactly at that peak spot, can be very difficult. Some inspections, it's no problem. The accessibility to the part is very easy, and the environment is not too difficult to work in. Maybe the surface conditions are quite good. But there's certainly a lot of inspections out there where, as a technician, you've got your arm inside something, wrapped around something. You may be dangling from a rope. You may be harnessed to the side of a building. There's both environmental and inspection concerns that may make it very difficult to even peak up the signal the first time, but certainly holding it in place while you're then manipulating the gain on the instrument can be a real challenge. And so a really nice solution to that kind of a problem is being able to make a gain adjustment either on a live signal or on a frozen signal. And this is something that's really only available as a result of some of the recent development in modern instrumentation. Now, making an adjustment on a frozen signal like gain definitely causes concern among most inspectors. This is something that, from early on we're taught is not something you're able to do. Gain is a live type of adjustment. And especially when we start talking about this being a result of a digital instrument, people start to associate this with digital gain, and that causes even more concern. Digital gain a lot of times evokes this idea of digital zoom on a camera. So most of us have had the experience with some of these point-and-shoot style cameras where you have a certain amount of optical zoom that's available to you, and that reproduces whatever image that you're looking for really, really well. But as soon as we get into that range where it's digital zoom, you can immediately start to see that the picture becomes more pixelated, it becomes fuzzier. It's not ideal if you want a really clear version of the image, like we see here, this picture of this ladybug. And so what's really important to understand is that gain adjustment in a modern flaw detector, it does use a small amount of digital gain, but very, very insignificant amounts of digital gain that would cause that kind of pixelation. Analog gain is still the most, or sort of the highest contributor of the gain adjustment, the amplification, even in modern digital equipment. But there is a way that we're able to use modern technology to still achieve the idea of gain adjustment while frozen. So this is a fairly generic block diagram of a more modernly designed receiver and amplifier in a flaw detector. And what we see here is that the signal will be received back through one of these green transmit-receive jacks. But as soon as it comes in, this is still the analog signal, as soon as this comes into the flaw detector, it actually gets routed to 3 different channels. In this case 3, the number may vary. And these are all processing the signal in parallel. And in these channels we have analog amplifiers. So each one of these channels is going to use analog amplification, standard gain, to increase the level, or in some cases decrease the level of that analog signal into different sort of windows, so that we now have the exact same signal from the same transducer, but we have it available to us at different amplifications, different levels, all at the same time. And in normal use, in live use, the instrument will then look at those 3 channels in this case, and the instrument makes an intelligent selection about which one of those 3 needs to be used to most properly represent that signal on the screen. However, once we're in the frozen mode, all of these amplifications, these are still available to us. So we can actually dynamically switch between those different amplifications and make some small adjustments within them. And this is being reproduced back into the flaw detector as if it's a live signal that's coming through the same channel. So it really allows the full dynamic range of the flaw detector to be used in this frozen mode without losing fidelity, without losing resolution, without getting any kind of pixelation. It's a real true signal that's being buffered into these different channels. So while this is kind of a foreign concept to many people of adjusting your gain after it's frozen, when your amplifier and your receive circuit is set up in this way, in this more modern way, it's really a possibility to be able to do this and do this without detriment or without seeing any kind of decrease in your resolution or the quality of your inspection. And if we go back to our photographer example, our camera example, really this is very similar to taking the same picture simultaneously but at different optical zooms. So the application here, of course, would be that the photographer may or may not want a zoomed in picture or a zoomed out picture. And so instead of taking several pictures in series at different zooms, one picture would allow the photographer to collect all this data, and then when he or she is back doing editing of the pictures or getting ready to print them, they can make a selection at that point of which one of the pictures and which one of the zoom levels that they want to see. So here we have someone taking a picture of a bear, and they, of course, want to stay fairly far away from the bear, but in this example, we would be able to capture all three of these different zoom levels simultaneously, and all with the exact same resolution, the exact same fidelity, and simply select later on which one of the pictures we prefer as our print. And the same thing is possible when we're making gain adjustments on a frozen signal. So this has been a fairly good overview of a lot of the very impactful, the really important advancements that are made in much more modern conventional ultrasound for the pulsar circuit and the receive circuit. And this can really have a good impact or a good effect on virtually any inspection that's done with a flaw detector. And a lot of these also apply to, again, precision and corrosion thickness gauges that are more modern. Now if we take a look at some other capabilities of the instrument that have been improved that aren't sort of core representation, the first one that we'll bring up here is curved surface correction. And really this is an idea that's been around almost as long as flaw detection. And it's been a calculation that many people do, especially when you're working with cylindrical pressure vessels, when you're working in pipe and bar stock. The idea of curved surface correction is very simple. It's simply that when we're making an inspection on a curved surface, and in this case we're sending sound out to reflect off of this side-drilled hole, we want to make digital measurements of the sound path, the straight line distance that the sound travels, but also the depth to reflector from the surface and the surface distance from the beam index point on the side of the transducer. The surface distance here is the one that's most affected if this is a curved surface as opposed to a flat plate, because with the addition of the curvature, we can't assume that this actually adds a bit of material. It basically has that factor of pi where we start worrying about the calculation of the circumference of a circle. So if you treat this inspection as a flat plate and you want to find exactly where your defect is with respect to your beam index point, you're going to end up being a little bit short on the surface distance. So curved surface correction is a calculation that allows you to figure out exactly what the true surface distance is. Now if you're going to do this by hand, it's really a tremendous amount of work, and hopefully you've taken a trigonometry course recently or you're very proficient with math. It's not terribly difficult math, but it's very tedious to have to go through, figure out several different angles, angle of incidence, angle of reflection, the thickness of the part. We go through several different calculations, and that eventually will allow us to arrive at this surface distance S. But this is quite a bit of work to do manually. The advantage, of course, of a digital flaw detector is that it's a pulsar receiver front end that has a computer attached to it. And so we're able to do all of these calculations within the flaw detector and simply provide the surface distance value that's been corrected for the curvature of the part to the user without requiring this to be done manually. Now it seems this has actually been available for quite a while on digital equipment, and it seems like a basic concept. But it's actually surprising how many of the surface inspection companies that I've personally dealt with and other users that are doing inspections on piping and cylindrical bar stock on a regular basis and aren't using this correction. And it works very, very well. It's very easy to set up. And it's a real benefit, a core benefit to anybody working with those kinds of curved surfaces. But another major benefit of modern digital equipment is the way that it handles data. If we go back even as far as, or as recently as 5 years ago, for the flaw detector industry, there really were a lot of inspectors that were making reports on their inspections and providing that data manually. So, and today this is still popular or prevalent that that inspectors are going out, they're using the tool to find defects, but then they're handwriting inspection reports and they're drawing out the flaws on a scan plan or on a gridded weld. And then they're having to go back to the office and digitize that into a report to provide to their end user. It's becoming more and more prevalent that companies, either the end users or the inspection companies themselves, are pushing for a paperless approach to this kind of reporting. And that both helps the environment, that's sort of a global initiative for things that are going paperless, but it also really has an efficiency improvement to the technician's life and the company's life. If you don't have to go through the process of manually documenting something and then digitizing that manual documentation, that's a huge benefit. So as conventional ultrasound instruments are primarily measurement tools, and there's actually the potential that they could collect thousands, hundreds of thousands of thickness measurements and things like digitized or compressed A scans. There's a lot of data that's stored within the flaw detector that is possible to actually transfer digitally to a report without having to go through this manual process. Now, one of the obstacles, so one of the reasons, I should say, that this is important, one of the major applications is for large asset management. And a lot of times this is inputting corrosion survey information, thickness measurements into some of these third-party softwares that are tasked with overall management of an asset. Whether it's a refinery, whether it's an offshore rig, whether it's pipeline. These are just some of the companies, there's many more, that are making software today that do a high-level management of a particular asset or a group of assets. And one of the requests from the service providers that are giving NDT or doing NDT for these assets is the ability to sort of interconnect with these software suites and be able to dump data directly into them without having to go through a manual reformatting or a manual entry into these third-party software suites. But another reason to look at getting digital data easily accessible into a PC application or something like this is just from the standpoint of unique reporting. Whether you're a large service inspection company or a small one of the ways that you will typically differentiate yourself from another service company is the content and the quality of the report that you provide to your end user. So, of course, the end results of any inspection are almost always required to be documented. They need to be supported, so archiving of that data is very important. That helps cover liabilities, of course, especially in the archiving of that data. And really, the way that this data is represented and presented to the end user is a way to ultimately make money, and that's the service that our service providers are giving these end users. And so the more efficient that a company is with providing these reports, with completing the reports, with providing enhanced data within these reports that really provides confidence to the end user, the more likely these companies are, of course, to get repeat business and to frankly be paid faster if there's more efficiency in developing these reports. For a long time, ultrasonic instrumentation manufacturers were a little bit difficult in terms of the data that they provide. Speaking also for Olympus, we've been in a situation as well where data is stored within the instrument in a proprietary format, and it's not easily accessible to a third party or to the end user. There are several internal reasons to do this for a manufacturing company for UT instrumentation. One is that it forces the end user to increase the investment with that instrumentation company. Typically there's a PC software that's being sold along with the unit that that allows you to sort of decode this data. And it also prevents a little bit of competitive snooping into the file structure of the different manufacturers. But of course, these two things don't necessarily provide value to the end user, the instrument purchaser. It's much more for the manufacturer. And that can lead to quite a bit of frustration, especially in the world that we live in today, where interconnectivity of different devices, being able to look at different file types on different devices is basically expected at this point. So one of the nice progressions and enhancements of modern UT thickness gauges and flaw detectors is not only their ability to store high volumes of data, but also to provide that in a more open source format for general consumption. So some key examples of these file formats would be CSV, which is comma-separated value that can be opened in most spreadsheet programs. HTML, which usually is a format used when providing a report. Either some image file types, so either a bitmap image, a JPEG image, a PNG, there's lots of others, but these are very common image formats that can simply be used in almost any program, any reporting program. And there's another one, XML, which we'll talk about on the next slide, which is also very interesting. And so these file formats, more often now, you're able to store data on board the instrument and simply extract this data or export this data to either a removable SD card or a USB stick or some other removable memory, so that it's very easy to simply take the data from the instrument to a common platform back to a PC and incorporate this into a report. The XML data is actually very interesting. This is one that I'm personally very fond of. XML, if you're not familiar, very briefly, is a very common sort of data management format. It's used quite a bit in web design, it's other light databases. What this allows you to do is create basically tags or names for particular data values. So there may be in XML, you may be representing a gain value of 60, and you're able to tag that with the name gain, so that it's very easy for a third-party program to simply read the structure of the XML and then seek out the different tags that are associated with different values and extract that data. So XML can be very easily consumed and converted into a variety of different formats, and this is really great for both established third-party asset management programs like we've seen in the past or in past slides, or this can really be integrated into a very small automated reporting system that's sort of developed within a smaller service inspection company. So even things like Microsoft Word or Microsoft Excel can easily interpret and read XML, and this can be, it doesn't take a tremendous amount of engineering or coding capability to extract this data and automate this into a report. And in many cases, this XML data can then be imported back to the instrument, either for file sharing amongst multiple instruments or to develop inspection plans, inspection templates that can be imported so that a user is guided through the amount of data that they need to save. So XML in particular I find to be a very powerful tool that's being used more commonly in flaw detectors and thickness gauges in the modern instrumentation market. So we've come to the end of our webinar now. Thank you for attending and for listening for the last hour. And in conclusion, just to sort of summarize, we have a really, really nice enhanced capabilities in many modern flaw detectors, thickness gauges, but they're all things that are surrounding our conventional ultrasound needs in the NDT market. it's interesting that we can, after so many decades, manufacturers can still find ways to improve even the core UT capabilities, core pulsar and receiver capabilities that really lends to increased fidelity, increased quality of inspection for almost any application. Of course, with the increased computing power within these instruments, doing special algorithms, special calculations, special software features, there's almost endless possibilities in modern equipment for these kinds of these enhancements. But also, as we've seen with the data management capabilities, there's really an increased opportunity to allow these instruments to not only be a component of an overall workflow, but to really be an integrated part of that kind of setup, inspect, and report workflow that most NDT users need to go through on a regular basis. Hopefully you've learned something that you didn't know about what most people think of as just plain old conventional UT. In fact, there's a lot that's still happening with conventional ultrasound in the market, and it can be a really exciting and really useful progress towards better NDT inspections. So I want to thank everybody for joining again today. We actually have gotten to our 3 o'clock, 3 o'clock in the U.S., but the hour limit. Unfortunately, we won't be able to take any questions live currently, but as Greg stated at the beginning of the session, we do have all of the Q&A that you've written in recorded, and so we will make sure to respond directly to this Q&A. And with that, I'll hand it back over to Greg and thank everybody again for your attendance.
Thanks, Coleman. On behalf of Olympus, I'd like to thank all the attendees for joining us today and Coleman for his expertise and participation in today's event. We hope this material presented was informative and useful. This webinar, along with the Q&A, will be archived on our website at www.olympus-ims.com. There's a lot of archived webinars there from the past couple of years, so I would urge everyone to go and take a look and click on the previous webinars button and you'll see the list. A lot of information there. Everyone who registered for this event will receive a follow-up email with links to the archived presentation. That's going to do it for today. Thanks again for attending, and we'll see you again next time.